right, as you come in, try these problems out. I'll turn off the lights. So see if you can name those.
Do you want us to balance them out too, or do you just want the names?
What do you mean by balance them out?
Like how it's chlorine 2 on there, do you want us to do like the switch over method that we were doing Monday?
Yeah, except, well, maybe I confuse people, right? Because the switching method is better when you're going from like names to formula.
Okay, so you, okay.
All right. What did we get for the first one, this FeCl2?
Iron chloride.
Iron, but then what else do we need to put in there? Iron chloride. But what's the problem with iron? Yeah.
You just need the 2 numerals.
So we need our Roman numeral. And so this is where you could use kind of like the reverse swap trick to remind yourself, oh yeah, this is a 2+ ion, and it balances out, right, our -1 chlorine. So that looks good. And so then what do we get for this FeCl3? So now iron 3 chloride, so good. So again, that's why it's important to make that distinction since different formulas. And what about this one? So tin, and then this is one of those weird ones. So tin, you want to star it on your periodic table because it can have multiple oxidation states. And so what is it in this one? So balance of charge. So what is oxygen? What's oxygen's charge? So -2, so -2 times 2, right, that gives us -4. So then 10 is what to balance it? So +4, so then we can use our Roman numeral. And
the balance, what number equals the balance would go in the parentheses?
yeah, so whatever, or this is the oxidation state. So yeah, it's the number that's balancing. And so let's take a look at this tin one, because this is one where, right, what happens if we try to do the reverse swap trick? So there's a 1 here. And so you might get 2 plus 1 minus. And so when you see this, right, and you've kind of backed it out, the first thing that you want to check is, well, is this charge what the oxygen is? And so that's kind of your first hint is, oh, this isn't right. And so, right, we'd said it was -2. So instead, now we need to multiply everything by that factor. So that gives us our 4 plus and 2 minus kind of back out. So again, these are oxidation states. So 4 plus for tin, 4 minus for oxygen. And then what about this last one? What do we get for the name?
It's cobalt, and then I was confused on if it's like nitrolide or nitrogen oxide.
So nitrogen, it's the same. This one always confuses people. I don't know why. So nitrogen, right, we just change the ending to "ide", so it becomes nitride. But then this is cobalt, so we need to add something to it. So we need to say oxidation states. And so what's the charge on nitrogen? Its oxidation state? So -3, and so nitrogen is -3. What does cobalt have to be? So our positive. Any questions about these ones here? Questions? All right, so we're going to keep practicing, but now we're going to kind of introduce a slightly different level of complication. And so I'll hand out our polyatomic chart. So I apologize, it's not the greatest resolution. I couldn't find. Oh,
Some of us have grabbed. Yeah, I already got
Oh,
it.
who didn't grab a polyatomic? And did you go get your polyatomics already? And so this is just another list. And so it has all your charges here. So they're in like kind of rough order. So these should be the same thing. It's just on the left side, they're in like alphabetical order. And yeah, actually I'm not sure what order they're. Oh, one of is like by alphabetical by name, and the other is alphabetical by compound, I think. And so you can use other lists. And so let's just define what a polyatomic ion is. So a polyatomic compound is a compound that is covalently bonded but has an overall charge. And so as we progress in the course, we'll be drawing polyatomics and other Lewis dot structures, but let's just start with a simple one. And so this could be as simple as hydroxide. And so hydroxide, you can see it on your chart. So there it is, hydroxide, OH, with a negative charge on it. And so we could draw the Lewis dot structure for it. And so let's at least kind of go over the basics on how to do this. And so what you need to find is our total number of electrons in our system. And so this is just the valence electrons plus or minus, depending on the situation, the charge. And so what I mean by that is, so if we look at oxygen, right, our periodic table, 6 valence electrons, so it brings that to the party. And then hydrogen, of course, brings 1 valence electron. And then we have a charge, and so since it's a negative charge, I'm going to add an electron to that. So for bookkeeping, I'll put my charge there and then have 1 electron. And so then we have 8 total electrons in this whole system, and then you just want to draw them all together. So first I'm going to make a bond, kind of putting them together because they're bonded. So this is showing a covalent bond. And so my single line here shows 2 electrons, so 1, 2. Then I need to put in the rest, so 3, 4, 5, 6, 7, 8. So this is our polyatomic ion, and then again it has our overall charge, so you want to kind of indicate that with our -1. Or you could put the charge on the atom itself that it rests on, but that's kind of a little bit more advanced, so we can revisit that. But it's on the oxygen, so we could put our charge there. So either way, so this is showing, right, that our whole thing is charged with an overall sign. This is still showing that it has a -1 charge. I'm just showing that it's on the oxygen. So that's all our polyatomic means. Again, we'll get into the Lewis dot structure part as we progress. And so again, right, we have our chart. And I'll point out some common ones, at least, for naming. So hydroxide, of course, comes up a lot. Cyanide also seems to come up. You don't generally work with cyanide salts, like in practice, because they could have the potential to be a little toxic. But you still might see that for naming purposes. What else? So carbonates are relevant. They come up a lot. Sulfate, you might have seen some sulfate compounds. Watch out for acetate. It might not come up too much, at least initially. It will come up in our acid-base chapter, but people always get confused with acetate because it can be written in the C2H3O2 form or the CH3COO form. I'll just draw out the structure for acetate. So CH3, so 1, 2. So that's acetate in its true form, so that's why it gets written funny. Other common ones are nitrate, so NO3 with the -1 charge, that comes up a lot. Notice you have very few positive ones, so you have ammonium is one of your few cations, and then technically also this mercury as well. So this is mercury 1, but it's complex as this dimer. So mercury 2 with a 2 charge, so each one is mercury 1. Oh, and then phosphate, so this is also really common, so this PO4 3-. And so for the most part, you'll just want to consult your chart, you know, until you become more familiar and start to kind of memorize these polyatomics. And so let's see if you can practice naming them. So we have all our same principles, right? So we're still thinking, well, if I have a metal that has variable oxidation states, right, we have to state that. And so now instead of saying like chloride, though, now we just name the anion or whatever the appropriate polyatomic is. So try these three on your own, see if you can figure it out. What do we get for this first one? Any thoughts?
Potassium, thorium oxide, but I'm a little confused on the parentheses still.
So potassium, and then, so you have this Cr2O7. So did you find this in your polyatomics? What did we, yeah. Hannah, or I forgot, I'm like blanking on your name. Emma. Yeah, the dichromate. So these could be tricky, right? So you might have to kind of stare at it for a little bit and see what your options are. But yes, you should have found the dichromate. And then we can always double check that everything was written correctly. So notice dichromate has the -2 charge, which balances with that potassium. So that looks good. So those are tricky. I might maybe star those if those tricked you. So don't let those chromates mess you up. What about this next one, Mg with this OH? Yeah, Hannah? Magnesium hydroxide, that looks good. If I could spell. Magnesium hydroxide. So excellent, so another group 2 metal this time, so we don't need to say anything about its oxidation state. And we found our hydroxide. And then just note, when they wrote the formula, right, we have our parentheses around our whole hydroxide, saying we need 2 of them. And then what about the last one? I haven't heard from that side of the room either. Iron nitrite, but then what do we remember about iron? So it's one of those with variable oxidation states, so what do we need to add? So the Roman numeral, so then nitrate, we have 3 of them. We can go back to our polyatomic since, you're just seeing this. So nitrates, -1, there were 3 of them, so -1 times 3, that gives us, right, a -3 charge here. So what does iron have to be? So +3, balance that out.
What did you say iron is a variable?
Variable oxidation state. So remember, it's in the transition metals, so it's over anything that's in our transition metal has variable oxidation states, except for silver and zinc. Yeah, the few exceptions. Other questions about those? At least for now. So more polyatomics.
Except for silver and zinc, you said?
Yeah, so silver is always 1+ for our purposes, although you find that that's actually not true. Silver has more oxidation states, but again, for our purposes, and then zinc is always 2+. Let's see. I think we just have naming practice. Before we go off on naming practice, though, let's cover some other random bits in your chapter. So then it kind of throws in there on how do we name these aqua compounds. And so let's look at some examples of this. So nickel chloride. And so what this means is that sometimes we have water that actually binds to the metal and is involved in our crystal structure. And so we can kind of confirm this obviously from a crystal structure, but we don't have a crystal structure. We can still tell that just from the properties. And so this is nickel chloride, and it's 2 different forms. And so nickel chloride, and this would be nickel 2. So nickel 2 chloride, if it's anhydrous, so anhydrous specifically means no water, so there's no water in this. So it's a yellow powder, and you could probably grow some nice yellow crystals from that. And then notice it turns into this green looking compound once it's the hydrated form. And so this is hexahydrate. So hexa meaning 6, and so we could then name it. And so we'll learn how to name it as well. So here it is on the Wikipedia page, and I'll put it on the notes as well. And so they have nickel chloride, and then there's this little dot. And so it's kind of hard to see. Some students get confused about that. But it's just this little dot there, and that dot signifies that the water is complex to our nickel chloride. So it's essentially part of the compound and part of the crystal structure. And then you just put however many waters are on there. And so, right, we had said hexahydrate, so that hexa is 6. And so there's many other compounds like this. So we can practice naming. So we want to be able to either write it or, of course, write the name. So then nickel, still 2 chloride, but now we just add hexahydrate.
And then there's a dot only when it comes to water.
Yeah, you basically only see that with water, which is kind of strange too, because like other things can complex, like ammonia and hydroxides and other things can act as ligands, but it's, yeah, mainly with the water where they use that dot notation. So see if you can write out the word formula for this one. So I'll give you another practice. So this is another common salt. And sorry, I should have shown this. So we could also see this where you have like 1 molecule of water for every 2 molecules of a substance. So that's where you get that weird half equivalent. So that would be hemi. And then the rest are probably prefixes you're familiar with. So mono for 1. I haven't seen this Sesqui in practice is 1.5, so same sort of thing. I can't think of a sesqui example though readily, but then 2 is di, 3 is tri, 4 tetra, 5 penta, 6 hexa, 7 hepta, 8 octa, 10 nona, 10 deca, so etc. So just, the prefixes you're probably familiar with. So try to name this one.
Will you go to the chart for a second?
Oh, yeah. So what do we get for this one? Oh, sorry, question. Oh, yeah, go for it then. Magnesium sulfate heptahydrate. Perfect. And so good job, right? So you had to find your polyatomic sulfate. So is that SO4 with that -2 charge. So we can see why they were in a 1-to-1 ratio. Excellent. Let's try the opposite. We'll do one example. These aren't too bad, but just so we feel okay. So try to, oh, I went the wrong way, didn't I? I wanted to go the other way. My bad. I'll try another one. So copper, 2, we'll do sulfate again, pentahydrate. I guess I'll put up the tin one, even though I had wanted to go the other way. Just so you can see more examples of these. What do we get for this formula?
Cu2
Oh.
SO4 and the dot and then 5H2O.
So double check, right? Maybe let's do some scratch work because you have copper 2+, but then what's your charge on your sulfate? 2-. So, right, we don't need to put a superscript, or subscript, to balance it out. So they're already happen to be balanced, so copper 2 plus, so okay, 2 plus oxidation state, sulfate -2, already balanced. And we could use our swap trick to help us. So we put our 2, but then, right, they have a lowest common multiple of 2, so then we can get our formula written there. Does that make sense? I know that can get a little confusing. Does that make sense?
To a certain extent.
Yeah, we'll keep practicing. And then, what do we get for this one? Do you have an answer, Cheyenne? Yeah, so tin chloride and then dihydrate, but then what do we need to add? I think you forgot one little part. So what was, remember what's tricky about tin? So start if you haven't. Yep, so tin 2 chloride. So it's one of those ones where we have to specify the oxidation state. And so I'll maybe remind you all again. So thallium, lead, tin, those are the big ones that have multiple oxidation states that I think you'll see.
So how do you know which oxidation state?
So then you have to base it off of the formula. So then if we go back, right, so she was, oh, if I could find my work here. So then we were able to figure out that it was 2, right, because there were 2 chlorides there. Yeah, so then it goes back to, okay, well, chlorine is -1, so -1 times 2 is -2. So we had a +2 to balance it. Excellent. And then the other thing that your chapter kind of like shoves in there is the acid naming. And acid naming, in my opinion, is kind of, I mean, it's like you just kind of have to brute memorize it, which isn't like the greatest thing to tell students necessarily. And so you have your ions, and yeah, like I said, it's not very intuitive with your naming because you kind of have your strong acids, or your, let's call them, your halogen acids, and they're all named pretty similarly. So, right, you have HCl, HF, hydrobromic is written there, hydroiodic we could add. And so all these, how you name them is you just say this hydro. So this is hydrochloric acid. And then, right, you usually add acid to the name. So same thing, so that means that this HF is hydrofluoric acid. And then HI is hydroiodic. Iodic acid. And so, right, some of these follow that same naming. So if it's kind of simple, like this hydrocyanic acid, but then it's not entirely clear why these polyatomics then are named this way. So again, it's like you just kind of memorize it and know. And so your nitrite, so notice nitrite has less oxygens than nitrate. So nitrous acid isn't really found like commercially available. It's just something that forms and then decomposes. But then nitric, this is what you buy in a bottle and we use it in lab. And so that OS is for the lower oxygens, and then ic is for more. So you see that with the nitrous and the nitric acid. Then you have phosphoric acid, so this is pretty common. Same thing with the sulfite, sulfate. So you have sulfurous acid, with the less oxygens, and then sulfuric with the sulfate. And then this is also kind of weird. And so this again refers to the oxygens. So you have the two normal amounts, we'll say. So you have chlorite, which with two oxygens, chlorate. So you have chlorus and chloric acid. And then once you have one more, then it's per. So perchlorate, so perchloric acid. And yeah, perchloric acid is nasty. You wouldn't work with it anyways. And then if it has less oxygens, then it goes hypo, like lower, so hypochlorous acid for that one. So I would mainly kind of focus on like these simpler ones initially, and then write your nitric, your phosphoric, and your sulfuric acid. So those are the ones that you'll actually kind of see in lab. You started to work with them, and probably want to name them. Do we feel okay about acids? No, it's kind of more you just have to learn them. All right, let's do some more practice then. So let's see, let's just do the first four and see how we do on this part. Do we need more time or? Okay, another minute or so. So let's try this first one. So any guesses for it? So molybdenum. And then what do we need though? So I like, yeah, so molybdenum 6 sulfate.
So the negative charge of the sulfate, does it cancel out the six,
Yeah, well, it does, right? Because -2 on sulfate,
yeah,
so times 3, so that gives you -6. So then,
they cancel out, but then you still add the six to the,
well, yeah, because the 6 just indicates the oxidation state of the metal. So it doesn't say anything about having a charge, right? It's just saying this is the oxidation state of the metal. And so this is always like assuming a neutral. What about 2? What do we get for this one?
what is it, thallium nitrate?
Oh, try again. I like the 3. Yeah, you can't see. You got the 3 though. So titanium. Yeah, and I mean, you're sitting in the back, so hard to tell. So that's an I, so titanium 3. And then what did you say for the last part?
Nitrate.
Nitrate, perfect. And so our nitrate, right, we can look back, so that's NO3, -1, so -1 times 3 gives us our titanium 3+. What about number 3 here? We haven't talked about this situation necessarily, so this is an interesting one. Any guesses? Charlene, any guesses? Yeah, perfect. Sodium hydride. So sodium hydride. And so this is kind of unusual. You don't always see hydrogen acting like this, but it can bind to a metal and then it still takes that "ide" ending when it's in this metal form. And so sodium hydride is a common one. And this is a fun reagent, very flammable powder, so pyrophoric. It's this little powder thing, and if you put it in air, it ignites. And many a fire have been started by sodium hydride contaminated chem wipes that chemists have brought out of their glove box, and then your whole trash goes up. So, yeah, so you just want to quench your little trash from your glove box, wherever. And then, what about the last one? Yeah. Beryllium, sulfite, and then you said heptahydrate, right? That looks good. Any questions on that one? All right, excellent. So let's try the reverse now. And probably do 4 again. So now see if you can write the formulas, or we'll just do the first 4 there.
Is there a way to also put up the H2O?
You want like the prefixes? Is that what you're asking for? You want these?
Yeah.
I could paste them over here. I don't know if that helps. Oh no. No, let's try again. Just trying to put it, there we go.
polyatomic ions, it only has the I and the A. So is that different, or is it?
Yeah, so it's probably just the element, right? Arsenic.
Yeah.
So, yeah, let's go through them. So what do we get for 11 then? How do we write that formula? So VAS, and then, so you only have a 5 on the arsenic?
Yeah.
So we need to balance it. And so let's do some scratch work. So we have vanadium. So vanadium, right, they said it was 5 plus. And then if we go to arsenic, what's the charge on arsenic though? Right, so arsenide, so we have to go to our periodic table, so it's arsenic. So what's the charge on these? So -3. So now 3 minus. So now we can do swap tricks, so that's again, right, easiest way to solve the algebra, because we have x and y for our variables, so too many. So vanadium 3 and arsenic 5. And so that gives you a neutral molecule. So then just double check that, right? So vanadium 5 plus, so 5 times 3 plus 15. Arsenic -3 times 5, -15. Does that make sense? So then let's try the next one. So what do we get for this one? Well, because you said, it's, yeah, how you say it is fine, because, right, we would name it cobalt-3 nitrite. Yeah. So, yeah, it's awkward trying to, like, rename it without just invoking its name. So, yeah, how you said it was fine. So, 3 nitrites, and we can do a little scratch work just to verify that and make sure we're all on the same page. So, cobalt, right, they said it was 3 plus. Then you look on your polyatomic chart. So nitrite, I'll just do that so everybody can see. So nitrite, NO2 -1. So then if we go back, so -1, and then we can do swap trick to get 3 and 1. So that's what we had found. And again, you can kind of re-verify your algebra. What about 13? How would you write your formula? So Y, what? YB? I think it's just Y for its, and then, but then you said ClO4. And then do we need a certain amount of perchlorates? So this one was kind of weird. So what do we remember about yttrium, or finding it on the periodic table? It's a transition metal, but then this is one of those weird ones. So it's usually in the 3+ oxidation state, so same thing with scandium. I would probably not fault you on the exam if you had written yttrium-3. So to me, they should have put a 3 there, just so we were all on the same page. Otherwise, you had to know and realize, oh, yttrium is usually 3+, and you might want to write that. Yeah. So kind of in general, now I don't want to say too much, but these numbers can kind of match the oxidation state. So like scandium usually loses 1D, and then the S's, so it acts like a 3+. Titanium acts like a 4+, but that's kind of a little bit of an oversimplification. So, and then, right, these are 11 and 12, so they tend to act as 1 and 2, though. Anyways. And so then going back to writing our formula, so then we need 3 perchlorate. So that was kind of tricky since they didn't tell us the yttrium. And then what do we get for the last one? So AGP, but then let's do a little side work. So what's the charge on phosphide? So 3 minus, and then we said silver is usually 1 plus, so what do we need to balance? So we have a -3 for phosphorus, +1 for silver, so we could do swap trick, right? That might help. And so now we can see we have to have 3 silvers. On the periodic table that I gave you?
And if that's the case, then wouldn't, I mean, it would make logical sense to pick AG3 plus, right?
Yeah, so this is one of those ones. So remember I said silver for our Gen Chem purposes is always 1, but I had also right after said that that's not true. And so right on your other periodic table it's more complete, it does have those other oxidation states. I don't know why for Gen Chem they're always like, this is how you name it, we just assume it has 1 plus all the time, and that's like the naming convention that's taken. But yeah, I mean, you can already find exceptions to that.
So this class is always going to be +1.
Yeah, unless it would be stated, but yeah, you might want to write that. So for our class, right, it's always +1, and so we don't have that oxidation state on silver. But yeah, once you do like research or get into even organometallic chemistry, silver can do weird stuff. All right, I think we're probably out of time. So I'll go ahead and hand out your quiz. And so feel free to take a 10-minute break if you need a break. Otherwise, you can go ahead and get started on it. So again, open note, just don't ask Google or ch104 or anything the solution. You can look at your notes, look at your textbook, and obviously don't ask your neighbor either. There might be an extra, I'm not sure.
S orbital versus p orbital, is it referring to like spatially, or is it like equality?
Oh, so just like talk about it, either like how many can fit and what it looks
okay.
like. Yeah, it's kind of open-ended. So,
Okay.
yeah, however you see fit.